So while it appears we're 15 minutes behind schedule, I saw Billy's talk last year and adapted my talk to fit into the remaining space, knowing that everyone would need a break. Not that she would over, but that everyone would need a break after seeing that material, because it is fairly intense. So I'm going to talk about machine learning for mobile health. I'm going to start by dovetailing into what we just heard. So I'm going to start by relaying out adaptive interventions for you, and we're going to talk about where machine learning methods can be helpful within the sort of broader mHealth intervention design process. So what are the components that we just learned about from Billy and what we've seen so far in the first 2 days? The first thing is that whatever we're doing is built around individuals when we're talking about treatment, right? So there's a particular person that we're trying to help, as Marlin was describing yesterday. There's some outcome or set of outcomes, proximal and distal, that we might be interested in improving for this particular individual. And in the adaptive intervention setting, again, there's some collection of treatments or treatment options, a basket of intervention components, however you want to refer to it, that we've defined. And as the process that Billy just pointed out is a question of what to provide to who when in this sort of adaptive process. Right? And so in support of those decisions, the individual is embedded in some broader context, environment, sort of broadly construed. That might consist of elements of built environment, of family, and so on, that are external to the individual, that may provide, again, aspects of context that are important when we're looking at making decisions about what treatment components to provide to who, when. Right? And so what glues it all together is this idea of decision rules, as Billy was describing. So based on the context, whatever aspects of context we think are important, we will attempt to match the available treatments to those contexts and then deliver them. And that could be either to an individual. We could also think about interventions that actually modify the environment in some way. So you can think about intervening on families or social networks as opposed to just individuals, although perhaps your target is to see a particular improvement in outcomes for an individual. You could also intervene on the built environment. The space of interventions is quite broad. Okay. Now, when we're talking about adaptive interventions, this process, you can see there's a feedback loop here, right, where we're deciding what treatment to supply, we're supplying it to the individual. That's going to change context and change outcomes. But in this diagram, time's not explicitly represented, right, which is the whole point of what's going on when we're thinking about intervening over time. So this basic process of deciding what to do in a given context repeats through time, as Billy was showing. All right, and so depending on whether we're talking about intensively adaptive interventions, just-in-time adaptive interventions versus interventions that are being adapted at a longer time scale, the notion, sort of relevant notion of time might be different, but that's not so salient. So time here could be every minute, time could be week 0 and week 2, and so on. Right? But the idea is that we have this sort of repeated structure when we're looking at the adaptation process, that we need to decide what to do among some collection of options based on context over time. Okay. And then the next thing that's important to note is that obviously these different constructs, so the outcomes, the state of the individual, state of the environment, and so on, they're not independent across time. Right? So the outcomes that we're seeing are sequentially dependent as well when we're actually intervening, as are aspects of context, as are the state of the individual. We might have long-term, in fact do have long-term effects. So things like habituation, engagement are processes that typically are going to evolve over somewhat longer timescales than, let's say, the decision points in an adaptive intervention, a JEDI, where we're maybe intervening or have the potential to intervene multiple times a day. Okay? So this is sort of a big, messy picture of what's going on in adaptive interventions. The question that I want to get at specifically is, where can machine learning help? Right? So where does trial design of the form that Billy was just describing help? Well, it's designed to tell you what should go into your basket of intervention components and when you should think about using different components and in what context. Right? So what's left over? Right? So again, to summarize, the pieces here are outcome measures. The questions are how to assess or measure them. Right? So Nabil talked yesterday about sensing, so did Vivek. What kinds of sensing devices should we use? What can they measure? We heard a little bit about self-report as well, so the idea of ecological momentary assessment as methods of assessing or measuring either, well, in this case, measuring either proximal or distal outcomes. Right? So there's measurement questions there. There's the question of context. So what are the context variables that we're interested in, and then how do we assess or measure those? And again, we can think about the use of sensing, we can think about the use of self-report, lab tests. There are a variety of methods that we might use to go about measuring these context variables. There's a question of time points. How do we decide how many times we're going to think about intervening, either within a day or a month or a year, depending on what the time scale of the intervention is. So what's the frequency and what's the sort of location of those points in time? There's the treatment options, like I mentioned. What should the set of treatment options or intervention components be that we're considering? And then there's the decision rule, right? So how should we go about deciding what to offer in what context? So it's 5 questions that you need to answer. And again, as Billy was describing, the trial designs are answering questions about what treatment options to include. And they do that in a very specific way, right? So they're looking at what is the main effect or the marginal treatment effect for particular components over the population of individuals that you're looking at, right? So over your study population. We didn't hear too much about time points and sort of how to think about measuring outcomes in context, right? So what we'll see is that these are some of the places where machine learning can come in to be helpful and to complement other types of approaches. So I'm going to tell you a little bit about some of the branches of machine learning. So machine learning is a large research area. It includes multiple sort of subfields that address different specific sort of data analytic problems. There are sort of 3 large categories. The first 2 are what are up here. They're referred to as supervised learning and unsupervised learning. Supervised learning is about learning to detect or predict. So specifically think about detecting or predicting things like events or state of an individual. There are 2 subproblems in there. The first one is called classification. If what you're detecting or predicting is something that can be sort of set up as a discrete category. So for example, are you stressed or not stressed? Are you smoking or not smoking? That's a classification problem. If what you're looking at is a variable that has sort of a continuous level, so if you think about weight or height or blood pressure, blood glucose, something like that, those are continuous values or real values, and what you have is a regression problem at that point. If you're trying to predict blood glucose, let's say, based on other factors that you can more easily measure, you have a regression problem, right? In the unsupervised case, this is about learning to organize and represent data. So there's no input-output relationships. We're not trying to predict anything. We are trying to organize data, let's say, by clustering. This has applications in areas like digital phenotyping. How do we find subgroups within data? The other large problem category there is called dimensionality reduction. So we have large-scale data for collecting mobile sensor data. We might have many observations from a single device or from multiple devices, digital breadcrumbs, all the things that Donna was talking about yesterday. How do we compress it down to a more compact representation that we can either understand or visualize or build something else on top of? The third sort of main pillar of machine learning is an area called reinforcement learning. This problem is about actuation. Right? So we had detection and prediction, we had organization and representation. Reinforcement learning is about actuation. So how do you learn to act optimally by trying different things, basically? So reinforcement learning is set up with a loop that sort of looks like this. You have a learner, an algorithm, it's often referred to as an agent. That agent gets to interact with an environment by taking different actions. It gets to observe the state of the environment, and based on what it does, it receives a reward signal. So something that tells it how well it's doing. Based on that reward, it can update how it actually acts in the environment. So this maps onto the sort of last of the problems in the list that I had up around decision rules. And so now I'm going to talk about how we map some of these machine learning ideas into problems around adaptive interventions. Right? So again, if you take this reinforcement learning loop and as your agent, think of this as your adaptive intervention. Okay? You interact with an environment that consists of the individual, the other aspects of context, so both environment or family, social networks, whatever you're observing and having an effect on. The reward signal that you can use here maps directly into this idea of proximal outcomes. So if you're trying to nudge people to improve physical activity with walking suggestions or stress reduction or something like that, the proximal outcome that you have, what is the level of stress that you're seeing? What is the person's wait, or what are the steps that you see in the next half hour, can form a reward signal that you can use to further adapt the decision rules. So the way this would integrate, think of a two-step process. We have the MRT kind of design or SMART to pick an initial basket of interventions. If you look at something like text messaging, that's ridiculously broad. So how do we optimize that for a specific individual? What specific messages from a collection are we going to recommend in a particular context for a particular individual? Right? So you can sort of perform this online fine-tuning within categories, right? If we're talking again about something like messaging, where we're going to look at what kind of emotional valence should the messages have such that they have maximal treatment efficacy for a specific individual. So this is a personalization process that overlays the question of what works best on average for a particular population. Right? So I'm not going to focus here on reinforcement learning. This is work that's sort of just really starting to get going within mobile health. So Susan Murphy's doing work in this area. Billy mentioned Susan previously. There's lots of work in this area going on inside machine learning. This is the sort of broad area of methodology that people use for game playing. So if you're looking at learning to play chess or learning to play other sorts of computer games, this is typically how it's done. Right? There are other kinds of methodology that you can use for this process of learning how to act. So system identification and control systems engineering is something that Daniel Rivera is going to talk about later in the Institute. It answers the same kind of problem. How do we behave optimally in the environment? And so I won't focus on this one. I am going to focus, though, on one of the supervised learning problems. And just to come back to this list, so this idea of how do we sort of further adapt and refine decision rules, ML can have some bearing there, but that's still a relatively new area of inquiry. I'm going to focus up here at the top. So how can machine learning help us when we're looking at outcomes and when we're looking at context? Right? I'm going to focus specifically on instances where we're interested in discrete events in terms of outcomes or context. So think about, I'll use smoking detection as a running example. But there are many other problems that have the same kind of structure. And if you have a continuous variable, again, like blood glucose or percent body fat or something like that, it works very similarly. Okay? But I'm just going to focus down on this one very specific problem. And one very specific machine learning sort of context. And it's going to cover both things that you might like to predict or infer or detect, whether it's something that you consider to be a context or whether it's something that you consider to be an outcome. And one of the things that you'll see repeatedly in mHealth is that there's a lot of fluidity between what's a context and what's an outcome. And so if we're talking about physical activity, steps in the previous 30 minutes is context, but steps in the next 30 minutes is an outcome. Right? And so what's an outcome and what's a context changes as you slide along through time. Okay? So it shouldn't be too surprising that the same kinds of techniques are going to be useful when we're looking at context and outcome. Right? So it's an inferential problem. What's happening? What is the state? What are the events that are occurring for both of these categories? Okay. So methodology, right? The question here is measurement. Right? Think of it in that way. How do we measure or assess a particular context or a particular outcome? We've already heard some different options for doing this. You can use self-report, various forms of surveys, ecological momentary assessment, and so on to answer this question. Basically ask people, right? If you want to know behavioral state, if you want to know, history of activity, what people are eating, you can just ask them. If you ask them in the moment, that's ecological momentary assessment. You can also do things like look at labs. So if you want to know blood glucose, you can perform an actual lab test to see what's going on. The last category, and what's of most interest here, is the use of sensor data, right? So looking at smartphones, looking at wearables, as Nabil was describing yesterday. So this question of how do we map sensor data into context and outcomes of interest is the question that we're going to focus on. And that sometimes that gap can be relatively small. So when we're looking at what we can sense and what we want to infer, and sometimes it can be large, right? So if we're looking at detection of eating or detection of cigarette smoking using a wrist-worn accelerometer, what we're looking at is, based on the hand gestures that we see, can we sort out what's eating, what's smoking, what's drinking, what's adjusting your glasses, what's scratching your nose? Right, that's the classification problem that we're attempting to solve. And if all we have is a 3-axis accelerometer, all we can see is linear acceleration. If we have a 6-axis where we have a gyroscope and an accelerometer, we can see a little bit more. If we have a magnetometer, we can see a little bit more. But we still have a relatively large gap to make up between what are we actually sensing? Linear acceleration, rotational acceleration, orientation relative to the Earth's magnetic field. Seems like how are you going to get it whether you're eating or drinking based on those quantities, right? So that's a sense in which there can be a substantial gap. And this is the problem that machine learning attempts to solve in this space. Right? So based on underlying sensor data that we can actually collect, how do we bridge the gap between what we can sort of immediately sense and the outcomes or contexts that we're ultimately interested in inferring as they relate to health and behavior. Right? Hopefully I've convinced you that that gap can be large. Okay, so I'm going to throw up some definitions as we go through here. There's going to be a little bit of math. I know we have a mixed crowd. Some people will be more comfortable with the math, some people less so. I'm also going to look at saying everything I'm going to tell you, I'm going to show you in two different ways. First, we'll look at some math. Second, some sort of geometry. So the interesting property of machine learning is that you can interpret just about everything geometrically, and we can make nice pictures in 2 dimensions to understand what is happening. And the connections between the math and the geometry, again, if you get the math, you can see the connections. Otherwise, if you're more comfortable with the geometry, that's fine. They're both completely valid sort of tools to use to understand what's going on in this space. Okay. So the abstract problem that I want to start with is this idea of building what we'll call an event detector. Okay? So we'll start with this idea of what is the event detection problem. And again, this is a problem that sits inside the supervised part of machine learning, where we will attempt to learn a detector that will issue detections. Right? So what does it mean to issue a detection? So the idea here is, let's imagine we have a dynamical system. That's just some system that's changing through time. That system has some state. That state, again, is changing through time. At every time instant t, the state of the system is defined and assumed to be visible to us. Given some numerical representation of that state, and again, we can't necessarily represent everything about the state, but we'll have some numerical representation. What we want to do is infer whether or not a particular event of interest occurred or not at each time point. Okay? So that's a very abstract problem. Let's look at a specific instance of the problem that we'll use as a running example, smoking puff detection. Okay. So in this problem, the idea is, suppose we have data from a respiration chest band sensor. So this picture in Billy's slides already. So this sensor produces a signal that is proportional to the area of a cross-section through your chest, where the chest belt is positioned. So you get a waveform that varies as you breathe in or out. As you breathe in, you get a decrease in amplitude. As you breathe out, you get an increase. Based on this waveform, for a given respiration cycle, what we're going to try and decide is whether or not that respiration cycle corresponds to a natural breath or to a smoking puff. Okay. We'll use this as a running example all the way through. So our problem is we have this chest belt. It produces this one-dimensional signal. And from that one-dimensional signal, we want to figure out which individual respiration cycles are going to be smoking puffs and which are not. Okay. Is everybody happy with that? So that's our general problem. We want to detect events. Here's our specific instance. We're going to attempt to detect smoking, smoking puffs. So we're going to build this detector together over the course of the next couple of minutes. Right? So the first thing, as Nabil described yesterday, we'll want to look at some data. And using the data, sort of visualization of the data, we need to sort of get a handle on what sort of aspects of the signal are going to be useful for answering this question, are we seeing a smoking puff or not? So I'm going to show you some data. And the first question is going to be, where are the smoking puffs in this data? Okay, so we're looking at actual data from an actual sensor. Okay, so I want you to take a second and then see if you can spot the smoking puffs. Ready? Okay, go. Okay, so the point of this is that this is what the computer actually sees, right? These are the readings off of the respiration chest band. Should never forget, when we're talking about data visualization, we produce representations that are easily consumable by us, by humans. But when you start looking at building algorithms over top of raw data, this is what the computer sees. Right? It sees the sequence of numerical values that were recorded, and that's all. So if you stare at this really hard, you can start to see that the sequence is sort of monotonically increasing along the first row here, and you'll see that it actually is periodic, but you have to look really hard to see that. Okay. You stare at this for a while, you can see the patterns. So that's not super useful when we're trying to analyze data ourselves. So what we want to do is produce some sort of a more interpretable plot. So here's a typical line graph. Here the unit on the x-axis is seconds. We're looking at the respiration waveform data. Can anyone spot where a smoking puff might be in here? Now that we can actually see the waveform. This is still too hard, right? So does anybody know, how many respiration cycles do you have per minute, typically? 12, yeah, about 12, that's right. Yeah, so we need to zoom in. If we want to actually see the waveform, the shape of the waveform for an individual respiration cycle, we have to zoom way in, because they're all basically smashed up against each other. So if we take a little piece of the signal and we expand it out, now we can actually see the structure of individual waveforms. So the baseline here is at about 2000. So every time we sort of go up from that baseline, come back down, and go back up again, that's a cycle. Okay. So who wants to suggest where we might have smoking puffs here? Yes, go ahead.
So there's a cycle that's up to, let's say, 2400, and that looks like, and down to 1000. That looks like a tidal volume, and then you have one that's stretching up to 2000. I'm having trouble reading it back there.
Yeah, sure.
Right around just before 320 milliseconds.
Mm-hmm.
That peak is probably the inclination and exhalation of
Yeah, that's exactly right. So if we look at the structure, we can see that there appear to be two different categories in this data. There is a set of peaks that are substantially lower. There's a set that are substantially higher. If you look carefully, you can also see that the duration, so the time, the length of the period is longer for these higher amplitude peaks as well, right? So Nabil was talking a little bit about this idea of features and featurization on top of sensor data, and that's exactly what we're looking at here, right? So we have the underlying waveform. The question is sort of what are its salient properties with respect to smoking? And the one that jumps out immediately is that you tend to have higher amplitude when you have cigarette puffs. Why is that? That has a mechanistic interpretation, right? So when you're taking a drag on a cigarette, you're going like that. Okay, so it produces a respiration waveform that both has longer duration typically, as well as what we'll call a higher stretch, where we're going up higher in amplitude, coming down lower in amplitude, right? So in this first process, sort of first stage of the process of building a detector, that idea of knowing sort of where are the positive events, so where are the respiration cycles that correspond to smoking in the data set, and then how do they differ from the non-puff? So everything that's not highlighted here is a non-puff. Right? So once we have that idea of way to numerically represent the instances, we can take them and map them into this space. So what we're going to do is sort of discard all the information about the specific shapes of the waveforms, and we're just going to map them into this simple space where we have duration on one axis and we have stretch on the other. So again, duration is how long from, let's say, peak to peak, or from 0 to 0 is the waveform. And then stretch is what is this amplitude difference from the peak to the bottom of the trough. Okay? So if we've got a sequence of these instances coming in, we can sort of embed them in this duration stretch space. So here's one that has relatively high duration and relatively high stretch. This one has low duration and low stretch, and so on. Okay? So if you have a whole bunch of data, we can do this for all the points that we have, and we embed them all in this space. Okay? So when we're constructing our detector, doing it directly over top of these variable size respiration cycles would be difficult. Here, everything now has a fixed size. Right? It's embedded in this two-dimensional space where we can sort of easily visualize what's going on. Right? The next step in terms of actually building a detector is to keep track of what was smoking and what was not smoking. Yeah, question? Yeah, so again, so that question, that segmentation question, so the question is how do you decide on the chunk, right? So the way I operationalize that is that we're looking at sort of zero crossings against a baseline. In this particular example, this is a little bit ad hoc, but the way you would do this is to use a bit of a smooth version of the signal, and you would look at these baseline crossings. So that's an important point where we're going to look at building a detector on top of segments. You can end up with sort of error propagation if you get your segments wrong. So if you have lots of noise in the signal or in your signal, you have to be careful about how you do things like pull out these segments. There are lots of ways to define the units that you are going to analyze when you're building an event detector. Another way to do it is to look at picking out all of the peaks in the waveform and put a fixed size window around them. You can do that as well. You can then featureize that window. So there are a collection of problems around segmentation that are also interesting, but for now, we'll just use this sort of basic operationalization of this idea where we'll look at zero crossings to define segments. So we end up with a feature space that looks like this. It has a labeling. So if we're running a lab study, people were smoking, we were observing them, we were taking video, we went back and we annotated it in the way that Nabil described yesterday. we could produce a picture that looks like this, right? Where we have the embeddings of the individual waveform components, the individual events, defined as respiration cycles operationalized in this particular way. And then our problem is to sort of induce a general rule, right? So based on the stretch and the duration features of these instances, how should we classify them? So what parts of this duration stretch space should we consider to be smoking puffs, and what parts should we consider to be non-puffs, okay, or regular respiration cycles? That's the detector learning problem. So the detection problem is to say, for a given instance, is it a puff or a non-puff? What we'll define to be the detector learning problem, or the detector induction problem, is given a data set consisting of examples of puffs and non-puffs in our chosen feature space, how do we decide on a rule that maps other points to detection decisions? Okay? So again, then if we receive a novel example, then we can put it into our feature space and classify it, right? Issue a detection for it. So what we want is something called an event detection function, right? So a function that takes our input, we'll put it into the feature space, we're going to apply a rule to that particular mathematical representation of the instance, and we want to produce a decision, right? So here we'll say 1 is, let's say, puffs, and 0 is non-puffs. So in our color coding, 1 corresponds to red, it's a puff, right? So what we want to do is find a function that operates like this, okay, where we give it numerical representations of our instances, and it gives us back yes-no decisions for puff, no puff. Okay? And in particular, we don't want that just at particular points in that space. We want it for every point in the space, right? So our function has to be able to take it has to be able to take any value of stretch and any value of duration and return to us a decision about what was happening, right? Was the corresponding instance a puff or a non-puff? Okay? So that's the, again, this is sort of the mathematical form of the thing that we want. What's the geometric form of the thing that we want, right? So in this stretch duration space, what the detection function corresponds to is basically a coloring of the space. So we can use the event detection function, we can apply it to every point in the space. We'll get the stress, or we'll get the stretch in duration over here. We'll, at this particular spot, we'll apply our detection function. It will tell us, is this a puff or a non-puff? And then we can color the entire space by doing that over and over again, right? So here's an example of what event detection function could look like, right? So it's a map. It assigns every point in the space blue or red for puff or no puff. Is this a good detection function given the data that we have here or not? No, right? So it's not bad. It only makes, relative to these data, it only makes 2 mistakes, right? So this red point is being predicted as being blue, and this blue point is being predicted as being red. So it's okay relative to these data, but it's not great. Right? Here's a better one. Okay? So this particular event detection function correctly decides that all the red points should be red and all the blue points should be blue. And further, it will give you a detection for every point in the space, right? Which is what we want. Okay. So we just saw this idea that if we have a discrete collection of options, okay, I have a collection of detection functions, I can evaluate them all and decide which one I think might be better, right, or the best. Right? Can anyone suggest a criterion that we might use to make that decision? Given a collection of these detection functions and a data set consisting of labeled examples for puff, no puff, how might we decide what is the best choice? Okay, so sensitivity, specificity, something simpler. What's the first thing that you would think of? Accuracy, right? So if we just count up the number of mistakes that we make, that's a good sort of first order thing to look at in terms of is one of these functions better than another, right? So if you can look at precision, recall, you can look at sensitivity, specificity. It depends on how you're going to operate the detector. Do you care more about true positives, false positives, and so on? But we'll just stick with this idea of accuracy to get started, right? So accuracy, again, just the number of points that are correctly predicted to have their true classes. Okay. All right, so we can sort of perform this process imagining that we have just a discrete collection of these detection functions, and we're going to select the best. We'll need a rule to do that, so let's say accuracy is going to be our rule, right? So we could evaluate all of them, and we could use that to pick the function amongst a set of these functions that performs the best in terms of accuracy. Right? So this notion of a model, so Donna was talking about models yesterday, and the specific notion of a model that we're interested in is a set of detection functions. Right? That's the way to think of it. So that could be a discrete set where there's just a finite number of options, and we're going to pick one of them, and that's our problem. That turns out to be highly impractical for lots of reasons, right? So when you actually go to solve these problems, you're not going to propose a set of discrete hypotheses about what the right event detection function is, and then choose amongst them, right? You need something that's more flexible than that. So instead, what you typically do is define a mathematical model that has some parameters that you can adjust that defines the space of event detection functions that you're willing to consider, right? So this is a basic linear model. What it says is we're going to take stretch, multiply it by a weight, take duration, multiply it by a weight, compare it to a threshold. If it exceeds that threshold, then we'll say it's positive class, and if it doesn't, it's a negative class, okay? Or the no puff class. So the set of all possible functions that we're considering are all possible choices for these three parameters, W0, W1, W2, taking all possible real values, okay? So this is a mathematical description of the set of functions that we're willing to entertain when we go to choose the one that we think is best. What does this correspond to geometrically? I promised you I'd show you the geometry. So what is this? That set geometrically is exactly this set of functions where you attempt to separate the positives from the negatives, right, or the ones from the zeros, using a straight line. So this mathematical description of the set of functions exactly describes all possible straight line boundaries between classes, between event types. Okay. And again, the machine learning process, you can think of it as just how do we find the best specific event detection function amongst some set of candidates. And again, it's pretty clear how to do that when you only have a discrete number. What's a little bit more challenging is how to do that when you have, in this case, an uncountably infinite number of possible functions that are under consideration. Right? And so this is where machine learning algorithms come in to attempt to explicitly choose these unknown parameters for you as a method for choosing the event detection function itself. Right? So, yeah, go ahead. Yeah, that's a great question. So the question is, what happens if you have a bunch of functions and they all perform equally well? Right? So in this, this is sort of the mathematical definition of this process of selecting the best function. So this term on the right-hand side is just counting up the mistakes. So it's looking at when the prediction f of x is not equal to the known value y, and we're just summing that up. So this is counting errors, basically. And what we're saying is, what are the parameters that minimize, what are the parameters w here that minimize the number of errors? And so Billy's question was, what happens if there's more than one function that minimizes the number of errors? Right? So one easy observation to make is that if the data that you have in your feature space are actually separable by a straight line, then there are in fact uncountably infinitely many straight lines that separate them. Okay? So we could take this line, we can also sort of look at all sort of possible small rotations and translations of that line that keep the data correctly classified or keep the detection decisions correct. They all have zero error or perfect accuracy. And so based on just looking at accuracy, we wouldn't have a method for choosing which one is best. Okay? So you need a slightly more refined notion of optimality to break ties. So one thing you can do is break ties optimally. Historically, there were methods that effectively did that. Their performance, so I need to jump ahead here a bit, but their performance on future data, right, is what you really care about, and that's what you really need to take into account when you're breaking ties. So it's really this notion of generalization, not how well are we doing on the data we've seen so far, but how will we do on data collected in the future. Okay? So that's really what you want to use to guide this question of how to break ties amongst a collection of functions that otherwise have the same accuracy. Okay? So we'll come back to that point in a bit. Okay. So, sorry. Oops. Okay. So again, this is our sort of starting mathematical definition for how to think about finding the best function amongst a set of functions. And again, that set could be discrete. More importantly, it could be uncountably infinite, where the process of selecting requires sort of more sort of mathematical tools But the problem is the same, right? It's a selection problem. What's best amongst some set? And the only difference is is that set very large and countably infinite, or is it something that's finite? So I want to show you a demo, let me do this carefully, that illustrates some different classes of detection functions or classification functions. Right? So I'm going to simulate the data that we had up. Probably want to look over here. That monitor is a little bit washed out. So what we're going to do is just put up some points in this space to mimic what we had up for the smoking example. So we had a collection of sort of red points over here, right, in our duration and stretch space. And we had a collection of blue points down here. And what we're going to do is look at this sort of linear, what we're looking at is what's the optimal linear decision boundary, this class of linear functions, based on the data that we're sort of drawing into the space, right? So if we nudge the points up towards the decision boundary is going to sort of swing around. The coloring in the space here is indicating the distance from the point to the decision boundary. So dark blue is very far on the blue side, dark red is very far on the red side, white is sort of close to the boundary. Okay? So again, the process that we're illustrating here is what happens when you optimize out the parameters of this decision boundary, basically, based on the points that we have in our space. And again, depending on where we have our points put down, that determines where our sort of optimal decision boundary is going to be. Right? So then there's the question of what is the space of functions that we're talking about. So this optimization is being performed with respect to the space of all possible linear boundaries, like I was describing. That's a fairly circumscribed space. So it's uncountably infinite. There are uncountably infinitely many decision boundaries, but they're all straight lines. There are other ways to separate points in this space that don't involve straight lines. So in particular, we could look at elliptical contours. Okay? So what we're looking at here is, in fact, an ellipse. It just happens to also be very close to a straight line, so we can't really see its curvature. But if we push on this a little bit, we can attempt to start to see some sort of curvature in the space, right? So here's an instance where, let's see, if we push it a little bit more. Okay, so here's an instance where we can still perfectly classify all of the points in the space, but it looks like it's probably going to need a curve in order to do that, right? So if we switch back to the linear boundary, you can see we're making sort of just one error, but we can make the problem much harder where a linear method has sort of no hope of actually separating the classes out. So this particular class of functions will actually, let me show you just another example quickly. You can do something like have a ring of points like this enclosed by another ring, and we can separate those out like that, right? And again, if you go to something, what's the optimal linear model, it just sort of like throws up its hands and says, I have no idea, equal probability everywhere, okay? So this is just to illustrate this idea that there is a hierarchy of complexity classes of these detection functions that we can use. And it's not just a question of what's the best within one of these classes, but what is the right class that you need, right? And part of this question has to do with, based on the data you have, what's really signal, what's real structure in your data, and what's noise, right? So one of the key problems in machine learning is what's called overfitting. It's possible with these classes of functions to achieve zero error on any data set. So the last one that I'm going to look at, so the first one here again is the space of all linear functions. This is the space of all functions with elliptical decision boundaries. And then this is the space, this last one here parameterizes the space of functions with smooth boundaries, where you get to say how smooth you want the boundary to be. It doesn't say anything else about the geometry. So you can start to put, build functions with much more complicated structure, right? So this is no longer representable by the second class we were looking at that has to be elliptical. It's a single elliptical boundary. Here we can start to have all kinds of sort of substructures and subgroupings of points that do different things in different parts of the space, and still get zero error out, right? So one of the sort of primary problems in machine learning then, right back to Billy's question, what happens if there are multiple possibilities that all achieve zero error, is choosing this sort of right notion of complexity. So it's always possible to find a function that has zero error on the data that you have. That may not be the best choice in general, and the reason is that what we really care about is this idea of generalization. We don't actually care about what's going on in the labeled data we have. We already have the labels. We don't need a function to tell us what the right answer is. We already have the right answers, right? What we really care about is what is the ability of a trained detector to perform well on previously unseen instances. Okay? And so when we're looking at constructing these models, the typical machine learning black box is just taking the data that we have and returning to us whatever, whatever is the optimal element of that set of models, you need to wrap that methodology in another layer of methodology that's trying to decide how complex the function is that you need in the first place so that you actually optimize your generalization performance. Okay? So one of the interesting things about machine learning right now is that there's a broad space of toolkits that are available that will solve this specific problem, right, or some variant of this problem of what is the best detector in a particular set, or what's the best classifier in a particular set. But you have to be careful in that you care about this problem, right? What's going to happen in the future when you're looking at previously unseen instances. And in the mHealth case, this is where, generalization is where we actually take a learned system and we deploy it to an actual study population, or as part of our treatment package where we're looking at trying to predict, let's say, a context variable like are you currently smoking, or a proximal outcome like how many smoking puffs did you take in the last half hour. Okay, so again, you want to be careful about how the model is that you've learned is going to perform under deployment scenarios. Okay? So this is key. How am I doing on time? When are we out?
How much time do you need?
We're supposed to end at 10. Okay, so we're already 8 minutes over. I will wrap up quickly. So I'm just going to end by sort of showing you what the entire detector development pipeline looks like. Right? So again, the purpose of this is to bridge between whatever raw data we have, whatever sensing modalities we're collecting, and an outcome or a context of inference of interest. That inferential gap can be large or it can be small. In order to make progress in the problem, we have to take our instances and we have to come up with some feature space that we're going to use to represent them. We need to pick a particular model that we're going to use, right? And that model can be more or less complex. We have to figure out how complex it should be, and then we have to figure out what is the optimal detection function. And so when we look at the entire process, what we need to do is collect data, right? Our sensor data. We need to collect labels for that data. Vivek and I were just talking before we started about this problem itself. Right? So collecting labels is not a trivial problem. Nabil was talking yesterday about using video to accurately segment. This itself is non-trivial, right, in terms of how to think about effort allocation for problems of this type. So collecting sensor data, you need to deploy the sensors to people, you need to do all the data management side that was described. In the end, collecting the labels that go along with the data is often the more complex part of this data collection process, right? It's what are the annotations, when did the events occur? You're using self-report from individuals for that data. There are all kinds of considerations there. If you bring people into the lab, you're going to analyze video. That has more control over the context, so you have maybe limited ecological validity, although the quality of the data is better. There are all kinds of problems before you even start, right, in terms of how you're going to collect data. Often when you're doing field studies, the data are noisy, they may have missingness, you need to clean them or screen them before you can use them. There's the feature extraction step, like I mentioned. You're going to do some visualization, figure out what features might be useful. From there, a key idea related to generalization is the idea of data partitioning. So there are two different tasks that we're going to need to do. We're going to need to train a detector, and we're also going to want to evaluate its performance, right, with respect to a particular notion of generalization that we care about. Both are equally important. You don't just want to do this. You want to train something, and then you want to look at how well it's going to perform. Okay. So once we've sort of decided on a scheme to partition our data, we need to choose a model, like I was describing. At that point, this is where machine learning toolkits kick in, right? So everything you've done up to here is sort of on your own. Model classes, there are many different model classes that are available in modern machine learning tools. There are deep learning toolkits. There are more standard sort of classical learning toolkits that are available. I was using scikit-learn in the demo that I was showing you, which is a Python-based toolkit. The detector learning, the application of detectors is what's sort of inside the scope of these toolboxes. Everything else here is something that you need to think about. How you design experiments, how you featureize data, how you collect data, how you assign labels. This is outside the scope of the toolboxes, right? So you can apply machine learning at the level of, we have the data, we're just going to put it in, we'll drop it into a detector learning algorithm. It's going to give us back a model, we can deploy it. That's very dangerous. Okay? The reason is that you have to think about all these things very clearly, including this idea of how are we going to partition data when we're evaluating how well our method is learning. Okay? So this top part is the training phase. The bottom part, we'll apply our detector, we'll evaluate performance, we get some sense of how well it's working. If we want to go back and revise decisions, we can do that. We can go back and look at maybe a different model class if our model was too restrictive. We might want to go back and look for other features. Right? We can go back and extract a different set of features. We can run back through this process some number of times. At the end of the day, when you're finished with this, you have some notion of how well your system might work, and then you're going to deploy it. And so you repeat those steps. You're collecting data, cleaning data, extracting features, applying the detector, and then you can use it for inferring outcomes, looking at context, and feeding it into the sort of decision rules that Billy was describing as different inputs, or using it as outputs if you're looking at reinforcement learning, for example, as sort of part of your proximal outcomes. Right? And I will just say, I guess we'll end here. So this question of partitioning that I was mentioning is a really important problem that's sort of underappreciated. And the reason is that how you partition your data into what you use to train and what you use to evaluate needs to directly reflect the notion of generalization that you care about. Okay? So there are different kinds of designs, just like Billy was describing different kinds of experimental designs. There are different kinds of detector learning experimental designs for evaluating generalization performance that reflect different notions of generalization. Okay? So there's a design called within subject design, and the way it works is you take all the data you have, you take the first prefix of that data temporally. Let's say you ran a 1-week study, you take the first 6 days, and you train on that, and you make predictions on the last day. Okay, so it's a temporal split of the data. And so the question is, what is that design, when you sort of train the detector and then you evaluate it in this way, what is it measuring? It's measuring the ability of the trained detector to make accurate predictions on future data from the same person, right, because of the way you set up the experiment. Another kind of design is you take all the people in your study, you train a detector on some of them, and then you apply it on another set. So you're holding out data from entire people. The learning never sees data from a particular person. You apply it, and you estimate your ability, you estimate performance, and what you're measuring is how well does the detector generalize to new people that it has never seen before. These two notions of generalization are not the same. Okay, this is looking at how well do we work on new data from the same person. This is saying how well do we work on data from new people. Typically, performance here is much better than performance here because of issues of between subject variability. Right? Another kind of design is a transfer design. In the tail end of Donna's slides, there was the Betty Boop picture, hot to cold models. This is what this is about. Okay? So you use data that you've collected previously from one group of people to train an initial model, which you then refine using data from another person and then evaluate. It's called in machine learning a transfer design protocol. So you still use temporal training test splits for an individual, but your training data is coming from a larger group of people that you might have seen previously. Okay? So let me just back up. This is all just to say that the landscape here in terms of how to apply machine learning is fairly complex. There are decisions that you need to make that have real impact. And what they're impacting is how well you think you're doing at the prediction problem you're interested in. The worst kind of mistake you can make in machine learning is to think that what you have performs well and then deploy it and realize you were wrong. Okay? And that has to do with how the experiments are designed and how the models are evaluated. So if you do within-person evaluation, and you say this is all going to work, this is going to work great, and you apply it and you deploy it to a new set of people, and it turns out that those people didn't look like the people in your original training set, and your methodology for evaluating performance overestimated how well you were going to do on new people, that can be a large problem, right? You're going to waste money and time deploying something that doesn't work. So again, the machine learning toolkits are really focused just on this little box of learning the detector. There's this entire landscape of decisions that you need to make, right? So the reason why I didn't try to cover more than this and do a deep dive instead is to get to this idea that there is a lot, there's a fair amount of complexity. There are a lot of decisions that go into the application of machine learning that is beyond the immediate question of how do you choose the optimal detector or what is the optimal model. Okay, thank you.
Question for them.
Yeah, go ahead.
So you were showing the example of the pop marker classification in the beginning in 2 dimensions. I'm not sure if that's what, or if you maybe you use more dimensions in practice, but it kind of looks like the peak height would do pretty well in detecting that difference between smoking and not smoking, at least with the in-person level. Is that something you guys have
Yeah, so the question is, similar to Billy's disclaimers about what she was presenting, what I was showing you guys here in terms of the example for the puff detection. So this is related to a paper called puff marker that you can look up. This space that we were looking at, these are two of the more important features for this particular problem, the sort of duration and stretch features. The actual feature space that was used in the work was about 36 dimensional. Okay, so 36 features. When we're looking at building maps, right, we can visualize maps if we're talking about 2 dimensions. If we're talking about 36 dimensions, we can't visualize the maps anymore. But conceptually, what's happening when we're thinking about the geometry of spaces and the geometry of detection functions is exactly the same, right? So if you look at a linear model that looks like the one we had down here, that only involved duration and stress, or duration and stretch, but you have 36 different features you put in, it's still linear boundaries. Right? The fact that you have more features doesn't stop it from being linear. It's still linear in this higher dimensional feature space. So yeah, that paper uses a collection of features. You can sort of see what's there. Separating out amplitude, peak amplitude from stretch and things like that are sort of covered in that work, as well as a variety of other features that come from other sensing modalities. So that paper actually fuses across a respiration chest band and a smartwatch to try and sort of triangulate in on what is actually smoking puffs and what is not. It's a good question. Yeah.
So, here you had sort of 8 priority feature sets that were given. Can you use the data set to actually extract, unusual feature sets just by making combination permutations and then backward propagating to actually get a better prediction tool on your supervised set that you then take to your unsupervised set?
Yeah, that's a great question. So the question is, can we think about other kinds of methods for getting features? So let me just back up here to this slide. So this box, oops. So this box down in the corner, that's about dimensionality reduction, addresses part of that question. So often what happens, especially if you have a new sensing device or you have a new detection problem, you don't necessarily come in with domain knowledge where you know sort of where to look or even how to visualize or what's relevant, right? So there are methods inside this sort of dimensionality reduction corner of things that can take high dimensional data and then attempt to project it down into lower dimensional spaces. And you can think of those as sort of automatic feature learning or feature extraction methods. Right? There are also ways that you can set up your detector learning problem such that it attempts to simultaneously learn a detection function in some feature space and also identify what that feature space should be. Right? How many people have heard of deep learning? Everybody. Okay, that's what deep learning is, right? So deep learning is attempting to simultaneously learn a detection function in a particular feature space and identify an optimal space. So if you look at typical deep learning methods, deep learning methods for classification, the top of a deep learning model looks just like what I showed you, right? Typical deep learning models have a classification model at the top that is a linear function of a feature space that sits underneath. But that feature space that they're sitting on top of is some nonlinear transformation of underlying raw data. Okay? So the answer to the question is yes, you can use the data to tell you what are features that are useful for a particular detection problem. The problem is you need to spend labeled data to answer that question. Okay? So you should think about that for a second. If we're in a regime where collecting labeled data is hard, right? It takes a lot of effort. You have to worry about ecological validity. We can bring people into the lab. That has limitations. We can field sort of data collection in the wild, but we have issues with the quality of the data, the granularity of the data, and so on. Labeled data collection is hard in mobile health. We typically bootstrap studies with relatively low volumes. The puff marker data set is something like, I'm going to say it's about 600 positive examples of smoking puffs and 4,000 negative examples. Okay? When you're talking about those kinds of data volumes, that's not big data, that's small data. You need to be really judicious about how you use the data that you have to sort of bootstrap these learning problems. So in general, that's that kind of class imbalance with roughly 5,000 instances is quite low in terms of the application of deep learning methods. So you can get the data to tell you what model complexity to use, you can get the data to tell you what features to use, but in that process, you are spending labeled data. Right? Ultimately, what you want is a detector there are instances where, again, if you can leverage domain knowledge, specifically in mobile health, if you can leverage domain knowledge, if you can not spend labeled data learning things you already know, like what are potentially useful features, your end-to-end performance can be better. It's a tension between bias that you inject, and your domain knowledge is a form of bias. Bias isn't necessarily bad in this context, right? What we're talking about is what, a priori, what shapes of decision boundaries are better than others. So that bias can help you combat high variability due to low data volume, right? As the amount of data that you have access to increases, typically you're going to be better off with a deep learning solution that's figuring everything out on its own, right? But right now, for the most part in mobile health, we're sort of back towards the sort of low to mid data volumes for many problems. When you start fielding deployments for hundreds of thousands of people, you'll be in a position where you'll have data volumes to support deep learning. Just as a sort of comparison, the work in computer vision that led to a lot of advances in deep learning used a data set called ImageNet that was developed at Stanford. It's 1 million labeled examples. Okay. That was a benchmark paper. It showed that you could exceed sort of performance of hand-engineered features, all previous hand-engineered features on image recognition using deep learning, but it took a very large data set to have enough labeled examples to actually get the learning of appropriate feature spaces to work. Right? So in mHealth, it's not necessarily the case that you'll need 1 million labeled examples, but our experience to date is that we're slowly approaching the sort of lower limits of requirements for application of deep learning, and you can get it to do interesting things, but it requires more. It requires more than the usual sort of basket of tricks that people use in NLP and vision right now. That's a great question. All right, you should probably break.
Okay.
Okay, thank you.